Good, well, welcome back, guys, and as ever, I do hope you and your family are keeping well. So what we're going to do today is we're going to start the A2 topic on gravitational fields, and I'm probably going to split it into a few video lessons, not the whole lot in one go. So we'll start off with stuff you know, and then we'll make it harder and harder and more like A-level. Okay, so the first thing that you know about gravity is that it's a force. But what's important is it's a force between masses. So it's between masses. And there are other forces in physics. This is a fundamental force. You can imagine there are forces between charges. That's the Coulomb force. But we're particularly looking at the force between separated masses. And there's one other thing that's really strange about it. That if you think of electricity, okay, Coulomb forces, plus and plus repel, but plus and minus attract. So you can get both attraction and repulsion. But with gravity, okay, it's only attractive. Yep. Which is really strange. Okay. You don't ever have a situation where two masses in a gravitational field repel. I'm not sure we really know why that is, but you need to remember that because forces are vector quantities, and we need to get the direction of the force vector right because of the way the forces attract. And you'll see how that comes into being a little bit later on. The other thing that's really interesting about gravitational fields is they go out to infinity. Okay, so this idea that juniors often have, that you get away from the Earth and you become an astronaut orbiting the Earth and suddenly you don't feel any gravity, or there's no gravity up there, is complete and utter rubbish. If you think about it, how would the Earth stay in orbit around the sun if you moved away from the sun and suddenly gravity dropped away to nothing? Okay. The other thing, of course, we do at GCSE is we say that gravity has a certain strength, a field strength. Do you remember 10 newtons per kilogram? But it gets weaker and weaker as you move away from the Earth, as you move away from a mass. So at A-level, we're going to have to work out how strong gravity is further and further away. So we need to look at the maths of that as well. Not just the gravitational field strength, how strong gravity is on the Earth's surface. Now, what's interesting is, because this force, the force of gravity, goes out to infinity, it's very long range. So it's a force that goes huge distances across the universe. And a force that's long range is usually very weak. Okay, so let's just have a look at that idea. So you're saying, but gravity's not weak, for heaven's sake. We're stuck on the surface of the Earth. But just think about how much mass the Earth has to have to hold us onto its surface. Think about how much mass the sun has to have to hold the Earth in orbit. Okay, you need vast amounts of mass to get quite weak forces. So if I usually hold up things in the classroom, but if I hold up a small object like my pen, which is only a small amount of mass, I'm not suddenly hauled towards it and attracted towards it. Gravity is very weak, but it is very long range. Now later on we'll look at other fundamental forces of nature, and a good example, I suppose, is the strong nuclear force inside an atom that holds protons together, for example. They should repel because they're very positive. Now the strong nuclear force is very strong, but it's very short range. Okay. Electrostatic forces between pluses and minuses are very strong indeed. It causes your hair to stand on end and things like that. Electrostatic forces when you rub your hair, but very short range. So gravity, yep, only between masses, only ever attractive, and it is huge ranging. Okay, and therefore very, very weak. Now, what I thought we'd do is just very quickly look at something we would do at GCSE as a quick reminder. And what I usually do is I take an object, there it is, okay, I make that something like 2 kilograms, and I draw a force on it acting downwards, okay, and you'll notice I've given the force a direction, okay, and towards the centre of the Earth, if we're on Earth. And if we're on Earth, we say, okay, well, the weight of this, the force is 20 newtons, or thereabouts, I've approximated, okay? And you remember that what we've done here is it's not brilliant physics, but we've said the strength of gravity, okay, the strength of gravity, more correctly now, guys, the gravitational field strength. So how strong gravity pulls in this region around here on a kilogram, okay, is approximately 10 newtons per kilogram. And I'll write it in the slightly GCSE-ish way, like that. Okay, so it's easy. You've got the 20 newtons by saying that the weight of this, yeah, its weight is its mass times by what we call the strength of gravity. Now we correctly call it the gravitational field strength. Okay, so this is really important. Yeah, okay. This is really important. The gravitational field strength is not something about Earth. Okay, the gravitational field strength is a bit of a complicated problem for physicists because you can't know it. Because you might say, well, it's 9.81 newtons per kilogram on Earth, but what is it a bit further away from the Earth and a bit further and a bit further? What is it on the moon? What is it by the sun? What is it near a galaxy? So the gravitational field strength can have so many different values because it tells you this. It tells you how many newtons, I'm writing it in a slightly childish way, per kilogram at that point in space. Yeah? It tells you the force per unit mass. Okay? Now, I think at GCSE you just thought about it as a number, but at A level, I want you to think about, at any point, you know, where I'm holding my finger now, what is the force per unit mass? Okay? Now, we choose to measure force in newtons, and we choose to measure mass in kilograms. Okay? So G, yeah, G will always have the units of newtons per kilogram. Okay, so that's a quick and brief introduction to the sort of GCSE bits you need to know. Okay, and my plan now is to take this physics just a little bit further. Okay, so a bit of a recap of GCSE there. Now let's take this a little bit further. And I've done a little bit more writing here. Okay. What I've done is I've done a very simple kind of idea. It's still a bit GCSE. But don't forget for A-level, F equals ma. What I've done is I've said, okay, look at this thing. We've got a 2 kilogram mass on Earth, so feeling approximately 20 newtons force. What would its acceleration be if we released it, forgetting about air resistance? Okay, well, F equals ma gives us the acceleration. A equals F over m, rearranging it. And the acceleration will be our 20 newtons accelerating force divided by the mass. So we've got an acceleration of 10 meters per second squared. Okay, now this is interesting because if you look at it, G, the gravitational field strength acting on this mass, okay, and its acceleration are identical numbers. And this is not a coincidence, okay? If you know the gravitational field strength at any point in space, if you were to release an object there, okay, it will accelerate with the same number, okay? So if the gravitational field strength in my lab at the moment is 10 newtons per kilogram, if I drop any object, okay, forgetting about air resistance, it will accelerate at 10 meters per second per second. Okay. Now, I hope you're happy with the fact that if I take a bigger object, or more correctly, one that's heavier, it doesn't make any difference. So if I take 1 kilo or 2 kilos or 3 kilos, it doesn't make any difference. It will still accelerate at 10 meters per second per second. So what we're saying here is, if you think about it, that the units of gravitational field strength, newtons per kilogram, must be the same as the units for acceleration. So what I want you to do is stop the video for a second and just check that out. Okay, you can do your dimensional analysis. Can you show that newtons per kilogram is exactly the same as meters per second per second? Right, so I hope you showed that these two are dimensionally consistent and kind of measure the same thing, as it were. Just want to take things a little bit further now and say, okay, so how would you sort of measure G, the gravitational field strength, if it's different everywhere? So later on I'm going to show you how we would calculate it, but the way I'd like you to think about the gravitational field strength is how hard is a kilogram pulled down by at any specific point in space. Okay, so let's just have a little look at an example like this. So I'm going to draw the Earth, get a better pen. Okay, so here's the Earth, blue planet, yep. And what we're going to do is take a mass and just put that mass above the Earth. So there we go, a little sort of weight above the Earth. Now, I hope you agree that it's away from the Earth's surface. Gravity, or the gravitational field strength at that point, will be weaker. And then you set up this rather sort of silly arrangement where you imagine you've got it hanging off a spring balance. So I'll draw the spring balance in blue. There we go, and it hanging off a spring balance. Okay, I know some people call that a Newton meter. Okay, and what you do is you look at where the pointer points on the little spring balance. Okay, and let's say the pointer points at 5 newtons. Okay, so we read off the spring balance 5 newtons. And let's say that this fella is 2 kilograms. Okay. Well, we immediately know that G, is the force per unit mass. Okay. And I know what I'm doing here is pretty obvious, but obviously you'll be working with more complex arrangements and numbers. And therefore, G is the force, 5 newtons, per unit mass, so we've got to divide by the total mass by 2. So the gravitational field strength at that point, will be 2.5 newtons per kilogram. Okay, now, easy stuff, sure. But I'm making a very specific point here, that firstly, we have calculated the force per kilogram. So later on in preps and things, I might give you the G value, and I might say, what's the force on the satellite? And you've got to think, G is the force per kilogram of satellite. Okay? The next important thing to say is, don't you remember that this was acceleration? So if I was to break the spring balance now and let the mass fall, okay, it will fall initially with an acceleration of 2.5 meters per second per second. Okay. Now, I've done one thing that's slightly weird here. I've measured the calculated the gravitational field strength, but I haven't put a direction on it. Okay, so I'm suggesting, because the spring balance is in this plane, that the force acting on this is that way. Okay, because it is a vector, and therefore the force acting on this is 5 newtons towards the centre of the Earth. Right, now, you're probably thinking this is very easy and you've got it all sorted, but I think you might have missed something. Okay, this is the force that this object feels due to the gravitational field strength at that point. Now, here we go. We have to imagine that this is a point mass, because I think some of you will be going, but FJ, what about the bottom of it? It's closer to the Earth where the gravitational field strength is stronger. And what about the top of it? Well, that's further away from the Earth where the gravitational field strength is weaker. Yeah, I get it. Okay. So all of the physics that we're going to do at this stage considers the object to be a point mass. So there we go, the centre of mass, or the centre of gravity, as I used to call it as a kid. Okay. The next thing is, don't get it into your head that this 5 newtons, in other words, caused by the gravitational field strength at that point, 2.5 newtons per kilogram, is due only to the Earth. Okay? It's I've given you the gravitational field strength, or we've calculated it, at that point. But could it be that number, which is quite small, even though the object is quite close to the Earth? And the answer is theoretically yes. Because might there not be a big mass up here pulling it upwards? And so we've actually done the vector addition, and we've said that the gravitational field strength is that value here, and that must be caused by all of the forces, all vector summed, to give a value at this point. Okay? So what I'm saying in a rather fiddly way there is the gravitational field strength here, and therefore that force is not just the Earth's effect or the two objects. Okay? There could be other things in here. So, for example, this force could be larger. It could be 6 newtons, but there might be a mass up there above my board that's causing this to be reduced. So our little measuring tool will measure not what masses are present, okay, not where those masses are directly. What it's saying is one thing. It's saying if you put an object there, okay, it will feel that force per kilogram, and if you release it, it will accelerate with 2.5 meters per second squared. Okay, so now for the last bit you'll be pleased to hear of this lesson. So what I'd like to look at now is the vector nature of gravitational fields, and we're going to describe how objects move in gravitational fields, where they kind of chase off to. And to do that, we're going to use the concept of gravitational field lines. So we're going to look at field lines. This is a really, really good way of describing how forces act in physics, and we're going to look at electric fields and things later on. Okay, so the way I always imagine this to begin with is, back to GCSE, is GCSE students have the surface of the Earth, okay, and their buildings on the surface of the Earth. There we go. Okay, and if you drop anything, so if you take an object, and here it is, and you drop it, it falls straight down. Okay, we're forgetting effects of air resistance and wind and all that sort of business. And if you climb up onto a taller building and you drop an object, it falls straight down. Okay, and I can continue doing this all over the diagram, and I can climb up a tower and Leaning Tower of Pisa or whatever and drop something, and everything just falls straight down towards the surface of the Earth. Okay, so what it suggests is that there are some mystery lines of force coming down towards the ground. Okay, and at GCSE, these lines that cause objects to fall, we can call the gravitational field lines. And these lines have a direction, okay, down towards the Earth's surface. Now, you'll notice something important about this diagram, okay? It's sort of correct at this level, but it's not really correct when we take it a bit further. You'll notice that the gap between the field lines is the same everywhere, okay? What that means is that if I drop something from a short height, 10 meters per second, or it feels 10 newtons per kilogram, and if I drop it from upstairs or higher up or up a tower or something like that, it feels the same gravitational field strength, it feels the same acceleration, or it has the same acceleration. Okay, so I should have drawn this a little bit more accurately, but the field lines are the same separation. So if you travel across here, every meter you travel across, you travel through the same number of field lines. Okay, so it's a uniform field. Okay, this is really important when we do electric fields. The field strength is the same everywhere. Now, don't get this wrong. Okay, it means that on the line, in the gap, above, below, everywhere on that diagram, okay, there are the same number of lines coming through per meter squared of area. Okay, the field is uniform. Okay. In other words, it has the same strength everywhere. Great. Fantastic for GCSE because we have 9.81 newtons per kilogram for G, or 10 newtons per kilogram approximately, and we don't do huge distances away from the Earth. Okay? But what I'd like you to do is to imagine taking this ground and bending it, okay, flexing it into a sort of circular shape because the Earth is curved, okay? And so we've zoomed in on a tiny bit of Earth and noticed the field lines sit next to each other and are parallel, but of course that isn't actually true. That if we were to back off and back off and back off and look at the Earth itself, so there's the Earth. Okay. Looking at it from a huge distance, okay, the field line comes in and comes in and comes in and comes in. But remember, bending the top diagram, okay, it's not uniform, okay? The field lines are not parallel. And at A level, they might say to you, draw on 6 field lines, okay, or draw on 8 field lines. If you do, okay, I'm going to say it once, I'll probably repeat myself. If they ask you to draw a number of field lines on an object, there's some things you've got to get right, okay? Firstly, draw the number of field lines they told you to draw, okay? Secondly, use a ruler, okay? Use a ruler because they're not going to be wiggly, yeah? And thirdly, you must put the direction on, okay? Because it's a vector. It's telling you, it's going to show you the force vector, the direction that things will go, okay? There is one other thing you must never do, okay? And I'll come back to that in a second. So I'm going to draw some field lines coming into the Earth. Okay, give me a moment. There we go, there's one. There's one. And I'll put another 4 on. There we go. There we go. And that one. Okay, I've done the best job I can quickly. And I've already lost marks because I haven't drawn the direction that an object would accelerate. Okay, so on every field line you draw, you must draw a direction. Okay. Now, if it was an electric field, it could be either way because they're attractive and repulsive. But the gravitational field is always attractive, so anything released here will go that way. Okay. Again, those of you who are a bit more advanced looking at this lesson, I am simplifying, obviously, because if you really understand your physics, anything that we drop here will fall that way, attracted by this field line. But of course, the Earth will be attracted to this object's gravity, so the Earth will fall towards it. Shall we just leave that for a minute? Okay, just hold the Earth static in space, and then we'll deal with what happens with two objects, because some of you might know about binary stars and all that sort of business. Yeah, we normally drop our pencil case. Yeah, we're not dropping a star or a black hole or something here, so it's okay to kind of hold the Earth still for a minute. Now, there's one other thing you'll notice that's really important on this diagram. The vector nature of the gravitational field is shown, but I have not drawn anything inside the Earth. Okay? Don't do it. Yeah? Do not draw anything inside the Earth, because this model only works with point masses. Okay? So if I back off and get off camera here, okay, and I go right to the back of my classroom and I go further and further away, that begins to look like a point mass, and I see these field lines going into it. Okay? But if you were to draw field lines going in towards the centre of the Earth, what you're doing is you're making the field lines get closer and closer and closer. Do you remember it's how many field lines pass through a metre squared? And as they get closer, there's more of them and more of them and more of them bunched up, and you're telling me that the gravitational field strength in the centre of the Earth is infinite. Okay, we're not in the black hole game here. If you think about it, an object in the centre of the Earth is kind of pulled that way and that way and that way and that way and that way by all the material above it. So there isn't going to be an infinite field there. It'll probably, I don't know, would it be left hovering if the Earth was not, hot inside and all the other problems? Okay, so don't draw field lines inside the object. Okay, the object's surface is where we stop. Okay, and we assume that that's like a point. Okay, I've kind of magnified it up for this. Yeah, so we know field lines have a direction. Okay, we know we must draw the direction on, and we know that as they bunch up, as we get more field lines closer together, the gravitational field is getting stronger. We know that we're going to consider these objects to be point masses, and you'll notice that from here outwards is the radius of the Earth. So if I get to here, okay, I'm going to describe that distance usually as distance r. R equals. It's a radius away from the point mass. Okay, so what you're seeing here is not a uniform field, okay, it's actually a radial field. Like spokes on a bicycle wheel, okay, but this is where my drawing doesn't really work very well, okay. Don't forget that in this plane, yeah, can you see the field lines going out like that and separating? So they're getting wider this way. But remember, there are field lines coming towards you as well. Well, actually, they're going towards the Earth, but I have to draw this in 3 dimensions. So there are field lines coming like this, okay, in this plane, coming from above and coming from below. Okay, so what I always try to do with students is I try to say, imagine these field lines coming in like that. Okay, and imagine those field lines coming in like that. So we've got an area here. So we're going to have to look at how the gravitational field strength changes with r, increasing distance, and they separate that way, and they separate that way. Okay, so they're going to get weaker with 1 over r squared, because we're kind of drawing out a square area here. Okay. It's not just a flat surface like that, and we'll deal with that a little bit more later on. Okay, so lesson 1 there on gravitational fields. I took you through GCSE and to some simpler A-level concepts. I hope you found that useful. Do pause and go back and check you know it all, and I'll see you in the second lesson soon.